Hey everyone, me and Arib are gonna take you guys through book four. Arib is gonna go through problem one. I'm gonna go through problem two, and yeah, let's roll with it.
Okay, all right. So again, it would be very helpful if everyone has the problem set open so you guys can look at the questions and the graphs that we're looking at. Okay, so problem one, gradient descent. So gradient descent is an algorithm that is used to minimize differentiable functions, as you probably know from a lecture. In this class, we'll primarily use it to minimize empirical risk, though its use is much more broad. In this problem, we'll explore a new loss function, see how our initial prediction impacts how much our prediction changes with one iteration. So consider a new loss function. So let's write it down. So we have loss function hy equals, and this is a piecewise function, which means that there's two different parts to it, depending on the value of our variable. So we have h minus y squared is a loss function when h is less than y, and h minus y cubed is a loss function when h is greater than or equal to y. Okay, so let's look at part A. Fix an arbitrary value of y. On the axis below, draw the graph of L of the loss function as a function of h. Okay, so I'll just redraw this graph here so we can see it. So we have L, H, Y, and then we have H, and we have Y. Okay, so what we want to do is we want to draw the graph of the loss function here. So let's look at the loss function. So the loss function is h minus y squared for values of when h is less than y, right? So basically for this part, we have h minus y squared is like less than y. And then for greater than y, we have h minus y cubed, right? So h minus y squared just means when the difference between h and y increases, we increase the function quadratic, the loss increases quadratically, right? So we can just draw, so this is basically just a quadratic function, so we have something like this, right? And now a cubed function, if you look up what a cubed function looks like, so we can see that whenever on this side when the difference is cubed for the loss function, we know that basically as you move further away from y on the right side, we increase exponentially in a cubed way for the loss, right? Now, if you look up what a cube function looks like, a cube function is basically just a steeper, like it looks how it looks. It basically looks like a steeper quadratic function. So what it would just be is something like this, where this side is steeper than on the right side, than on the left side, sorry, right? Because the cube function is steeper than a quadratic function. So that's basically what um, the graph of the loss function which look like as a function of x for this function that we have. Okay, let's look at part B. Okay. For any data set y1 to yn, the empirical risk r is 1 over n, the sum of the loss function of h and yi. Will be differentiable and convex, also known as concave up. This means the gradient descent is guaranteed to be able to find its minimum value. It might take many iterations or only a few. We won't do the whole algorithm, just one iteration for practice. Suppose our data set is 2, 3, 6, and 10. Perform one iteration of the gradient descent by hand on the empirical risk function RH for this data set, starting with an initial prediction of H0 equals 3 and using a step size of alpha 1 over 10. Calculate H1, the prediction after the first iteration. Okay, so for any problem like this to get to this point where we can make the next prediction, first we must calculate the derivative of the risk. Okay, so let's look at this. So we know that our loss function is a piecewise function where we have h minus y squared for h less than y and h minus y cubed for h greater than or equal to y, right? So if we take a derivative of this for each part of the function, we get the derivative of the loss is, so this just becomes 2h minus y for h less than y and 3 of h minus y squared for h greater than or equal to y. Right? That's just simple taking derivatives for both pieces of this function. Okay. So now using the sum rule of derivatives, so we have the sum rule of derivatives, we can say that the derivative of the risk is a sum of all the derivatives of the loss function for each value of y. So if we substitute our piecewise function in here, we get y equals 1 to n 2 h minus y squared for h less than y and for h greater than or equal to y. Right? Okay, so now we have the derivative of the risk. We're ready to start with gradient descent. Okay, so let's start with the first iteration where h of 0 is 3, right? So to apply the gradient descent update rule, we first have to calculate the derivative of the risk at h0, right? So at h0 equals 3. So what we can say is r of h0 equals r of 3, right? R of 3 is basically, we substitute our value in, so it's basically 1/4 of equals 124. And sorry, give me one second. Yes, so we know that, we get 4 from the value that we know that there's 4, that n is 4 here, since we have our data set is of 4 numbers. Okay, so we get 1 to 4 of I to 4, and the loss of 3 yi, right? So this basically will become 1 over 4 of the sum of all the losses from our data set. So we have L of 3 and 2 plus L of 3 and 3. So basically, I'm finding the loss of 3 and all of 80 as 3 with our data set of 2, 3, 6, and 10, right? Plus our loss 3, 6, plus our loss of 3, 10. Right? So if you calculate all of these, what we get here is basically, um, this is a piecewise function, so we have to do different things, right? So when h is less than y, we have to do a different function, and when h is greater than y, we have to do a different function. So breaking all that down here, what we get is 1 over 4 of 3 times 3 minus 2 squared plus 3 of 3 minus 3. So here I'm just substituting the values on the piecewise formula of the derivative of the risk, derivative of the loss, plus 2, 3 minus 6, plus 2, 3 minus 10. Right, so substituting all these values in, if you can make this calculation, we get minus 17 over 4. So we know that our update rule is, so h1 is h0 plus the step of alpha times the risk at h0. So what we get is, so h0 is 3, alpha is 1 over 10, and the risk at the derivative of the risk at h0 is minus 17 over 4. So what we get is This is basically 3 plus 17 over 40. So basically what we can say is the update from H0 to H1 is just adding this 17 over 40 number, right? So it's just this fraction that we're adding to 3 to get H1. Okay. Let's look at the next part. So let's see. For the same data set, suppose instead we did one iteration of gradient descent on RH, but starting at a different initial prediction, 80 of 7. Using the same step size of alpha 1 over 10, calculate H1, the prediction after the first iteration from this new starting point. Okay, so similarly as this previous part, we have to calculate R of H at H0 equals 7. So R of 7 equals 1 over 4 of I equals 1 to 4 of L7 yi. So similarly, we follow the same overall calculations that we did the previous part. I'll skip through those this time. This is the same steps we did last time. So what you end up is we get 30. Okay, now the same update rule. We see that H1 is H0 minus alpha times the derivative risk at H0. So what we get is 7 minus 1 over 10 times 30, which is basically 7 minus 3, so we get 4. Okay, so basically what is it saying is that when H0 is 7, H1 is 4. The next value that we get is 4. So comparing the answers, so let's look at part D. So I think this is something we can just talk about intuitively instead of writing it down. But let's see. So compare your answers to the previous parts and notice that the prediction moves only a little bit when we start at 80 of 3, but it moves a lot when you start at 80 of 7. Can you explain why that happens by looking at the loss function we're using? Okay, so we know that our loss function is a piecewise function, right? And looking at the graph, so looking at this graph from part A, we know that it is much steeper when h is greater than y, right? So we know that because it is much steeper, what we can say here is that basically, since it's much steeper to the right than to the left of left of y, this means that when our prediction of h is greater than a data value, the loss is significantly more, right? Because when our prediction is equidistant from the data value and in the other direction, right? So basically, like some prediction here. So let's say some prediction here from at d distance, and some prediction here at d distance. The prediction here is going to be much steeper than the prediction on this side, right? Because we have a cubed function instead of a squared function. So the risk, since it comes from averaging loss functions, also behaves like this, and increases much more steeply to for largest value of h than the smaller values of h, right? So for our data set 23610, the prediction of H0 for 3 is a bit low, but not that much lower than the minimum value of RH. So the slope of R3 is not that steep, right? When we use H0 of 7, the risk is an average of a cubic function since 7 is larger than most of the data points, right? So basically when we say H0 is 3, we know that there's 3 values that are larger or equal to 8. So we're going to use our squared function, right? When 80 is 7, we know that only one value is larger. So we're going to use the cubic function most of the time, right? So we know that the risk is going to be much more is when we use 80 of 7. So the slope there is very steep. This corrects itself quickly by moving rapidly towards the minimum value. As we can see in the gradient descent update rule, when the derivative is larger, the algorithm takes larger steps. Okay, so that's what we have for problem 1. Uh, Varun, you want to do problem 2?
Yeah, I can go over problem 2.
Okay.
So, okay, problem 2. we look at multiple linear regression. So what we're talking about is the notation and basic components of regression with multiple features. Um, the table below shows the softness and color of several different avocados. Oh, again, please have the group work open while we're solving this. Otherwise, none of this is going to make sense. Um, the table below shows the softness and color of several different avocados, which we want to use to predict their ripeness. Each variable is measured on a scale of 1 to 5, where 5 is the largest value. So softness having a rating of 5 means it's really soft, and then color having a rating of 5 means it's really dark green, so on and so forth. But yeah, suppose we decide on the following hypothesis function. Given an avocado's softness and color, we average these numbers to produce a predicted brightness. Part A questions if this hypothesis function is a linear hypothesis function or not. And a linear hypothesis function is one that takes in and transforms in some way, shape, or form its regressors in a linear manner. So when we're talking about averaging or given an avocado softness and color, averaging these numbers to produce a predicted ripeness, yes, this is a linear hypothesis function because we're taking half times the softness and half times the color and adding them together. This is a linear combination of the two features. Um, so taking any kind of um, uh, any number of the regressors and B transforming them in a linear fashion, as is this case, taking half of them. Yes, that constitutes a linear hypothesis function. The next step is writing down the hypothesis function as a function hx, where x is a vector comprising of x1 and x2. Um, and h of x is simply just half. It's just half of x1 and x2. So h of x is just 0.5 x1 and 0.5 x2. Just write it lower because it's too much to the right now.
Okay, sorry.
Yeah. Uh,
My bad.
yeah, that part is fine. Just write the super. Yeah.
Yep.
Yeah. Yeah. Uh, for part C, write down the feature vectors x1, 2, and 3 for the first, second, and third avocados in the dataset. These are really simple. You essentially look at avocado number 1, 2, and 3, and just construct the feature vectors from there. So feature vector 1 is 3 and 4, feature vector 2 is 1 and 2, and feature vector 3 is 4 and 5. That's basically it. Yeah. Just, yeah. Just be able to see that. For part 4, we're looking at the predicted outputs of these. So we're essentially taking half of each of the features in feature vector 1, and then doing that same thing for each of the features in feature vectors 2 and 3. Yeah. And that's just 1.5 plus 2, which is 3.5. And you kind of plug and chug with hx2 and hx3 to get 1.5 and 4.5. 4.5. Yeah, perfect. Compute the MSE. 4.5. Yeah. For computing the MSE, we're just gonna take our prediction, subtract. Actually, let's just write the formula down. It's gonna be 1 over
Yeah.
3 sum I equals 1 to 3 y cap minus yi whole square.
Can you say again? 1/3 I equals 1 of n or?
I is equal to 1 to 3 instead of 1 to
Okay.
3 because we know we have only 3, right?
Yeah.
Yeah, and then y cap minus yi whole squared. Whole squared. Yeah. So looking at this and just kind of plugging and pulling in values, it's 1 over 3 um, times 1 squared, which is, yeah, just write 3.5 and 2.5. It's fine. Uh, I kind of messed up. 3.5 and 2.5. Yeah, just 1. That's, which is 0.25, 0.5 squared, which is 0.25, and then hx3 minus y3, which is again 0.25 because it's just 4.5 minus 5 squared, 0.25. And so we have the values themselves, or the squared values, adding them all up gives us 1.5, and then taking a third of that gives us 0.5. So the final mean squared error value is 0.5. Just try 1.5 at all. Yeah.
Yeah.
Super. Yeah. So then for part F, we're going to construct the design matrix. And the design matrix is essentially just, it's going to be the column of constants for W0 in our W vector. And then the two features. So 1, 1, 1, 3, 1, 4, and 4, 2, 5. And 4, 2, 5. And the parameter vector W, part G. Yeah, the parameter vector W that we have for the problem is simply a function of this design matrix, and it's going to be 0 because we don't take in the column of constants at all. Don't use that at all. 0.5 and 0.5 for the first column of softness, I believe, and 0.5 for the second column. Uh, yeah, part H is just confirming that the design matrix times W, so XW gives us the y cap vector that we had before, and it does. Yeah, 3.4, 5, 0, 0.5, 0. And then just write is equal to y cap is equal to 3.5, 1.5, and 4.5.
Is equal to y cap, right?
Yeah, yeah. It's equal to 3.5, 1.5, and 4.5. And then
Mhm.
part I is writing down the observation vector y, which intuitively from the missing cap on top tells you it's the list of, or the vector of observed values that we have, which is just 2.5, 2, and 5. Yeah. Okay. Uh, for part J, we're calculating the length of the vector xw minus y, where xw minus y is just 3.5, 1.5, and 4.5 minus 2.5, 2, and 5. And we get 1, 0.5, 0.5, 2.5, 2, and 5. And then that gives us 1, 0.5, 0.5, or 1, 0, negative 0.5, and negative 0.5. Uh, yeah, it's minus 0.5. Yeah. And then you want to take the length of the vector, so just take the L2 norm and square root it. Yeah. Uh, that should give you the square root of 1.5. Yeah, perfect. And then part K, we're looking at the the relationship between the vector xw minus y and the mean squared error that we looked at in one of the previous parts. The length of the vector xw minus y that we had was square root of 1.5. Taking the square root of this gives you 1.5, and then taking the mean of this, which is 1 over 3, because we have only 3 data points, gives us the mean squared error of 0.5.
Sorry, can you repeat the last step?
Yeah. So, yeah, it gives us 1.5, and then you take the mean of this. You take a third
I
of
see.
this to give you
So this is
0.5.
the so this is the total squared error, right?
Yes, yes.
Total squared error. So the mean squared error is just
Yeah, perfect. Uh, yeah, notice that this has a relation to one of the problems that we solved in group of two, where we were looking at the error vector, the length of the error vector, and seeing if the W value that we actually had was the optimal W value. So you should be able to draw that relationship here. And for part I, part L, we're looking at we're sort of evaluating the hypothesis function that we have so far. So we're looking at, is this the best hypothesis function? And is there a better one, or is there a single best one or multiple best ones? And this is essentially the process of solving the normal equations that we have, which is just looking at x transpose xw is equal to x transpose y and getting the value of w from this. Uh, and this would imply that w star is x transpose x inverse times x transpose y, as you may have learned in lecture already. X transpose x inverse times x transpose y. Yeah, yeah. And the matrix x transpose x that we have is 134, 112, and 145 times the original matrix x that we had, which was 111, 314, and 425. And 425. And this gives us 3, 8, 11, 8, 26, 34, and 11, 34, 45.
let me go down.
It's fine. I moved us to like outside.
Oh,
Because
okay.
yeah, I don't want to like I said, keep saying it again and again. So I just gotta move this in. Yeah. And notice that this matrix is or like immediately noticing that this matrix is just um the elements repeated in some way, shape, or form, i.e., the first row is the first column, the second row is the second column, and third row is the third column, tells you that the matrix is not invertible. Um, this should tell you that the matrix isn't invertible, that the columns aren't linearly independent, so on and so forth. Uh, Intuitively, that tells you that there isn't a best solution for W star because the one condition that we had for W star, no matter how long the problem took, no matter how complex and how many rows and columns that it had, was that the matrix is full rank. The matrix X transpose X inverse is full rank. Um, this matrix X transpose X um, and ergo X transpose X inverse that we have is not full rank. Um, so that would tell you that there isn't a single best solution, and that's what we get when you solve this. for uh, uh, W star. This obviously isn't solvable by hand, but we kind of plugged it into Wolfram Alpha to give us a solution. We got 11 over 14 minus x3. Wait, do you want to write down the solution? Just say
Uh,
W star
yeah.
is
Oh, 1 second. Yep.
um 11 over 14 minus x3. X3.
Oh, you mean like,
I guess you can just call it like any variable, like alpha or something like that. It doesn't matter.
yeah.
Oh yeah. Um, 25 over 28 minus alpha.
Is that the bottom value or the right?
That's the middle value. That's the middle value. 25 over 28 minus alpha. And then the last value is alpha. Yeah. So immediately from this W star, you should be able to tell that the values aren't linearly independent, or there aren't independent values for each of the features that we have. And the reason this is true is because we're using the last value that we have for the last feature, which is just alpha, which you can denote it by any constant you want, and using that in the first two values for the two features that we have. So um, because that last variable is a free variable, it's not tied down by any of the other features, and it's not determined by any of the other features. That essentially tells you that we don't have a single solution. So assume x3 is 0, then you have 11 over 14 and 25 over 28. That would tell you one of the best ways that we have to do predictions is to scale the softness by a factor of 25 over 28 and add a constant factor of 11 over 14 and completely ignore the color because, that's how we arrange the groups. Uh, and yeah, that is problem 2. Please, let us know if you have any questions. Feel free to comment on Piazza or, let us know what you have. But
Actually, yeah, let me use, just to go by, let me use X3 here.
yeah, just that's what I was saying that for consistency, but it's too many.
And then what we get is, so we can use h of x here. Is 14.
25 or 28. This is when we have plus 0. Yeah. 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 This is when we have x3 as 0, which means we completely ignore the
Yeah.
color. Uh yeah, we completely ignore the color as a feature. Use the column of constant values in some way by multiplying it with 11 over 14 and adjust the softness by almost 1, so 25 or 28. We completely ignored one of the other features, and that's better than the original feature vector that we had. Note that this is only with 3 examples. This isn't with like a whole data set or whatever. This is just to show you guys the properties that we were talking about in class. But yeah, with that, I think we're done. So, see you guys soon. Oh, wait, Arib, do you want to say anything? I put us back in frame, so they can see us now.
Oh, no. Yeah, that sounds good. Yeah, feel free to make sure to pause at every point of these steps so that you can try to figure it out yourself. I think that would be best to have full understanding.
Cool. Yeah. Okay. See you guys for group 4.